Howdy, we are the Multi-Robot Senior Capstone Team, and this is our Project Showcase presentation. My name is Ryan Audix.
My name's Esteban Arispe.
My name's Christian Landry.
I'm Matthew Semper.
I'm Glenn Stearns.
I'm Taishan Zhao.
In our project, our main goal is implementing different components in order to allow for Turtlebots to move autonomously in a lab setting with no collisions. We started with taking the OptiTrack system that our sponsor bought and installing 3 of the motion capture cameras on walls surrounding our test area in the lab. These cameras were wired into a switch box via Ethernet cables and then connected to our central Windows computer. On that computer, we installed a motion capture software called Motiv to calibrate the cameras and to pull tracking information from them. Once we were able to set up a coordinate system with the OptiTrack cameras on the Motiv software, we were able to set rigid bodies with 2 Turtlebots by attaching 6 tracking markers on the top of them. Once that OptiTrack system was ready, we moved towards working on data communication component of our project. This relied on a high-speed Wi-Fi router we purchased to create a local network that would be able to transmit data from the Motiv to a new Intel NUC Mini PC that would act as the main brain for moving the Turtlebots. This mini PC would run off ROS and Ubuntu and talk to additional NUC Mini PCs that were set up on 2 Turtlebots. There we were able to successfully implement the data communication as we were able to pull in coordinates coming from OptiTrack. In order to test the successful integration of all these components and make sure pathing would happen, we found a pathing code online that would be able to take the OptiTrack data so that the Turtlebots could move autonomously. As you'll see later, this test proved successful, and the Turtlebots were able to move throughout the environment with taking data from the OptiTrack cameras towards a predetermined goal.
We want to remind you that this project initially started in spring 2020 with a previous senior design team. The previous team purchased the OptiTrack motion capture system, which consists of cameras, mounting equipment, markers, and Ethernet cables. They also purchased the HP central computer as well as the 2 monitors. The robots and Intel NUCs were previously purchased by the TAMU Center for Advanced Robotics. Our team's goal was to continue the previous team's work by integrating all of the previous provided equipment and to acquire any necessary equipment.
The first step in assembling our lab environment was installing 3 OptiTrack motion capture cameras in the room to capture the entire active space. In doing this, we first modeled an optimal layout in SOLIDWORKS using the manufacturer's field of view specifications and the lab room dimensions. Then, using a magnet, we located the building's metal studs and installed 3 degree of freedom mounts as close to our model location as possible while avoiding any studs. The mounts were installed using appropriately weighted drywall anchors and screws after consulting building maintenance, and the cameras were attached to the mounts via set screws. Finally, Ethernet cables were run through the drop ceiling in the room from each camera to a central switchboard that funnels the camera data into the motion tracking software.
The next step was to set up the OptiTrack Motiv software. We began by calibrating the cameras using the calibration kit that included a calibration wand and a calibration square. 2 calibrations had to be performed, with the first being the wanding, and so this consisted of walking around the environment while moving the wand in a figure-8 motion. This calibration gives the cameras a depth perception and will make them aware of their location with respect to the environment. The second was a ground plane calibration where the square was used to set the ground level for the environment, and it also set the origin of the coordinate system. After that, in order to differentiate the Turtlebots from other markers in the environment, we had to set the Turtlebots as rigid bodies. And so what this means is you basically set markers in a specific order or shape that the OptiTrack will always recognize as a Turtlebot. It also provides the Turtlebot with a front, which allows the software to provide angular direction based off of where the Turtlebot is facing.
To be able to control the Turtlebots, the Intel NUC Mini computers were all installed with the Ubuntu 16.04 Linux operating system. This is the latest version of the Ubuntu that is compatible with the Kinetic ROS distribution package, which we are using for our project. ROS is short for Robot Operating System, and it is an open source robotics middleware suite, which provides a set of software libraries and tools that allow for hardware abstraction in its applications. We then installed the Turtlebot specific ROS packages along with other communication ones for the specific needs of our project. Of the 3 NUCs, we had one which was configured to be the main workstation to be able to interface with the other NUCs controlling the Turtlebots and to collect the data from the Motiv software. The way the main workstation received this rigid body positional data from the Windows PC is through running a virtual reality peripheral network client program through which ROS was allowed to subscribe to this data being published over the network. This positional data, along with all other commands, are then transmitted from the main workstation to each individual Turtlebot wirelessly through our local area network using a secure shell cryptographic network protocol for all of our testing needs.
In order to test our environment and setup, we researched and adapted a couple of Python programs and algorithms from GitHub and modified them to fit our environment. We also had to learn how to stream the data that the OptiTrack Motiv software was reading onto the NUCs using ROS topics. The OptiTrack system provides positional coordinates in the X, Y, and Z linear directions, and also provides 4 angular coordinates. These coordinates have to be implemented into the code in order to send the correct commands to the robot. This process proved to be one of our most challenging and time-consuming tasks because it required a lot of debugging, trials, and error testing. The final algorithm rotates the Turtlebot slowly until it is facing its inputted destination. Once it is in an acceptable angular range, it slows down even more and then comes into a stop. The algorithm then makes it move forward until it reaches its destination. And finally, we decided to add a spin at the end to prove that the code worked correctly.